Okay. Just kind of abbreviate and write a brief description here. Objective 1, calculus versus precalculus. Maybe you could write that. Objective 2, the tangent line problem. And the area problem. Here's the thing. Really, this lesson, all this lesson is supposed to do is give you an idea of why we need to have calculus and not just precalculus. Precalculus is awesome. There's a lot of things we can do with precalculus. But not everything. There's a lot more things we can do with calculus. So it's good that you've had precalculus. It's prepared you. But forget about it. No, we're going to use a lot of it. But anyway, that's the objectives. Okay? So, what is calculus? Besides super awesome happy hour. Word for word, I want you to copy this. Nope. But this is actually a pretty good definition. Calculus is the study of mathematics of how things change. Okay? That is pretty accurate. How things are changing. Write that down at least. Calculus is studying how things change mathematically. Now I know you probably, well, I don't know for sure, but I would assume in physics, who's taking physics or taking physics right now? We talk a lot about position graphs and velocity graphs and acceleration graphs, right? So we're studying how things change. Okay? It's not just finding a slope that's static, it's finding a slope of a curve that's always changing, or finding volumes of things that's always changing. Precalculus is something that's static. You get an answer that's the same answer for the entire function, whereas in calculus things change depending on where you are in the function. So it is much more complicated, but it relies really on the basics of precalculus that you've already learned, which is nice, and the basics of algebra. Okay, but this phrase here at the end, precalculus is more static. You know what static means, right? Not the electricity, but static means yeah, it probably stems from that word. Static means not changing. It doesn't change, whereas in calculus, dynamic means it is changing. And I'll show you some examples of what that means here. Well, they will show you some examples. An object traveling at a constant velocity. So let's say you're driving down the freeway at 50 miles per hour, and it's not changing. Okay? And let's say you're driving between the hours of 1 p.m. and 2 p.m. at 50 miles per hour. Can you imagine this? If I were to call you at 1:30 and say, hey, how fast are you going? What would you say? 50 miles per hour, right? If I called you at 1:45 and say, hey, how fast are you traveling now? What would you say? 50 miles per hour. If it's a constant velocity, the velocity never changes, right? But what if you're accelerating? What does that mean to be accelerating? Some students have a hard time understanding this. If you're accelerating, your velocity is changing. It's increasing, right? So if it's a lot different of a question to say how fast are you going at an instantaneous point in time. Okay? Because if I call you and say, how fast are you going right now, by the time it takes you to actually look down at your speedometer, you're no longer traveling at the same speed that I wanted you to tell me like a half a second ago. Does that make sense? Yeah. Because you've already increased your speed, even though it's been a split second. So to find the instantaneous velocity if you're accelerating takes calculus. It's just a derivative. It's pretty easy. But do you see the difference there? That's called an instantaneous rate. Or like that. So the slope of a line can be analyzed with precalculus. To analyze the slope of a curve, you need calculus. That's one example. This curvature of a circle, I don't know if we need to really deal with that. But this right here, the area of a rectangle, That's pretty easy to find, right? How do you find the area of a rectangle? Length times width. That's pretty easy. But one of the big issues of calculus is to find the area under a curve. I'll show you what that looks like here in just a second. Okay. Precalculus is going to lead us to this in Chapter 1, the idea of a limit. Once we have a pretty good understanding of what a limit is, how it works, how we find limits, then we're ready to start talking about calculus. So Chapter 1, I guess you could say it still is calculus, but it's still more of preparation. Calculus is derivatives and integrals. That's really all it is. You've heard those words, derivatives, integrals. Okay? You can't find a derivative unless you understand what a limit is. Same thing with integrals. Okay? We're not actually going to be finding limits today. We'll talk about that on, what day is it today? Thursday? Not Monday. We don't have school on Monday. So Tuesday, I guess, right?
I labor on Labor Day.
You labor on Labor Day?
Consider it laborious.
Anyway, just take a look at the screen up here, guys. If I ask you to find the value of a function at x equals c, you look at the graph. Here's c. What's the value of the function? It's just a point on the graph up there. The idea of a limit is something different. And I am going to talk a little bit more about this next time, but just to give you a little preview, the idea of a limit as x approaches c. If I had an x value on the x-axis that's moving closer and closer to this value of c, okay, I need another pen, don't I, dang it? If my x value is here, then the f of x value is here, right? Just right above it?
Yeah.
It doesn't do two different persons, though. I wish that'd be cool. But try to imagine in your mind, as I take this, as I take this x value that's right here and move it closer and closer to c, what's happening to the f of x value that was right above it? When is it moving closer and closer to? That point, right? That's the idea of finding a limit, the limit of a function as x approaches a number. Anyway, we'll get closer to that on Friday. It's pretty easy to find the slope between 2 points of a straight line, yes? The change in y divided by the change in x? Yeah. That's not too hard, is it? But what we're going to see, I don't think in Chapter 1, what if I wanted to find the slope of this line right here that's tangent to the curve, and all we have is that one point? Do you see the problem? It's easy to find the slope between 2 points, isn't it? Or precalculus, or algebra, really. Is it easy to find the slope of a line if all we have is 1 point? No. Well, with calculus it is, but do you see the need for that? Okay, and at least the need for calculus. What would this be? This is like that example I was talking about of an instantaneous velocity. If you're accelerating and I say, well, how fast are you going right now? That's the equivalent to finding the slope of this tangent line at a particular point, which you would need calculus for.
Isn't it like if you move that point, you would just barely double slope?
Exactly. Okay, and I'll show you that on Friday. But yeah, what Kay was saying, if this point moved up over here, for example, now you have a slope that's negative. Okay? If we're thinking about this like an acceleration curve, you're accelerating, decelerating. Anyway, we talk a lot about that in calculus. We'll have plenty of time. We don't really need to talk about that. Here's what I was talking about with the area of a rectangle. Length times width, easy. Right? What's the area of this region? Okay? This is the fundamental of calculus right here, specifically the integral. To find the area of this region is easy to do once we learn how to take an integral. It really is. Okay? But without calculus, would it be very easy to find the exact area of this region? Not really. Okay? This might sound familiar to you physics people. Work done by a force. Isn't that something you talk about in physics? Things are much easier in physics with calculus. So much easier with calculus. The length of a line segment, that is so hard for students to remember from algebra. Do you remember how to find the length of a line? Or a segment, I mean? The distance. Remember that big giant square root thing with like x1 minus x2 squared plus y2 minus y1 squared? Anyway. You remember that. Shut your mouth. To find the length of a curve takes calculus. Pretty easy with calculus. Ooh, this stuff is where calculus gets fun. There is a formula to find the area of a cylinder, or the volume of a cylinder. We're going to learn how to find the volume of such three-dimensional objects like this. That's pretty cool, huh? Kind of looks like a vase, but this takes a basic level of understanding of calculus that really won't be beyond your guys' level. This is towards the end, finding volumes of solids that have been revolved around an axis. Anyway, so let's talk about the tangent line. Write this down, tangent line problem. The notion of a limit is fundamental. You don't need to write that down. The tangent line problem. So draw that picture as best you can. And be as accurate as you can. A tangent line only touches the outside of that graph. It can't cross through it twice. Just so you become familiar with terminology and how I would say things, this is a tangent line at point P on f of x. All right? The tangent line to the graph of f at P, or one of the problems we're going to have to do here pretty soon is find the slope of the tangent line at point P, just different things like that. We got it? Before I show you the next slide, can anybody think of a way to pretty closely approximate the slope of that line? We can't find the exact slope of this line without calculus because we don't have another point, but can anybody think of a way to get pretty dang close with only using what's given? Yeah. If we could find the y-intercept, yeah, we could if we could find the y-intercept. But since we don't know the exact slope of the line, we wouldn't be sure where the exact y-intercept would be either. Does that make sense? But that's a really good thought. That's a really good thought. What are some of your other? Right now, any idea is a good idea. Any idea is a good idea. What would be a way to approximate the slope of this tangent line at point P? What do you think? Think about it. Right now, any idea is a good idea. To find the exact slope of the tangent line, we possibly could try to find another point out here. Would it help to find another point on function f? Why not? Like, what if I put a point right here? You see where my mouse is? What if I found, which would be pretty easy to do, we could find the location of that point without much trouble. And what if I found the slope of the line? Where does the mouse keep disappearing? Dang it. What if I found the slope of the line between point P and this point right here? Would that approximate the slope of the tangent line very well? What if I put the point right down here? Closer, right? What if I put the point down here? A lot closer, right? Well, what if we just keep going and get closer and closer and closer? What if I choose a point that's 0.01 away from point P? You get pretty, what if it's 0.0001? How close can we get, by the way? We can get infinitely close. You know what that's called? The limit process. That's what this chapter is about. You know, you start out here, but we say, okay, what's the limit of this value as this point approaches that point? Okay? And if we find what the limit is, that's going to approximate. And in some cases, it's not going to just approximate. It's going to be the exact slope of the tangent line. But does that explanation make sense? Let me show you a visual. And all we're talking about right now is approximating the slope of the tangent line. So, let's make sense of some of these symbols here. First of all, a secant line is just a line that crosses through twice. So we have a secant line here. Does that look like it's going to be a very good approximation of where it is now? Probably not. Okay, but more important, I just want to make sure you're comfortable with all of this notation. Is this looking a little weird? I don't even know if I can zoom in on that. Let me see if I can zoom in on that, at least on the screen. Hey! Nope. Zoom in a bit more. I like this. Okay. Well, somebody said it. That little triangle. We talked about those last time. What is this? Read out loud. Delta x, or the change in x. Okay. So we started out originally with point C. So if we're talking about the coordinate location of this point, and this is something that really you're going to have to start thinking of. Instead of thinking about this as x comma y, it's not x comma y anymore. Okay. It's x comma f of x. Because what is f of x really? F of x is really just y. So really, we deal a lot with function notation in calculus. It's not x comma y, it's x comma f of x. So if this is point C, then the coordinate location is c comma f of c, right? All this is x comma y coordinate location, right? We okay with that? Now if I start with the value of c over here on the left and I have some change in x delta x, really try to think about this, you guys. You need to focus. Here we go. If this value is c, in terms of the x value, what's the value right over here? How far did I travel? If I started at c and then traveled all the way over here to the right, how far have I traveled? Delta x, right? So what's the x value right over here? C plus delta x. So if I'm talking about the actual physical, well, that's weird, the physical location of this point right there, what's the location of that point right there on the graph? What's the xy coordinate location? It's c plus delta x, comma, f of c plus delta x. Do you understand the notation now? And we are going to be dealing a lot with this. We're going to be dealing with a lot of deltas, because what is calculus? It's the study of change. And what does this mean? The change of x, and here we have the change in vertical distance. What's the change in vertical distance? You could call it a change of y, but now we call it a change in f of x. Okay, or f of c in this case, I guess. But that's what this notation is. Does that make it a little more clear? Hopefully. How do I unzoom? So, the best way to approximate the slope of a tangent line if you don't know calculus is to use this limiting process, where you drag this point Q closer and closer and closer to point P, where the secant line begins to resemble more of the tangent line. Okay? All this is how to find the slope. This is just the slope formula. So, this is an illustration of what I was trying to explain here. As point Q becomes closer and closer to point P, look what happens to that secant line. It drops down to resemble what? The tangent line. What is this process called? Taking a limit. Okay? The limit means as one thing approaches another thing, how does that change? That wasn't explained very well at all. As point Q approaches point P, that's one change, right? What else is changing? The slope. So as Q approaches P, the secant line approaches the tangent line. That's the idea of a limit. As x approaches this, f of x approaches what? You know what I mean? That's the basics of a limit. We had a question somewhere. I saw a hand right here.
So you're trying to get a point as close to P as you can, so that the line connecting those points is the tangent line?
Or as close as we can get to the tangent
the
line.
same point, so it's just one point almost, but not really.
Exactly. It's like 2 points, but not really, because like Kate said, couldn't we get infinitesimally close to point P? So if we are getting infinitesimally close to point P, then is there any discernible difference between point P and point Q if we continue to travel towards point P infinitely long? Eventually point Q and point P are going to be the same.
So then are you finding the slope of those points? Or,
We would be, say that one more time.
well, because, I don't know. So we're finding the line, right? The slope of that tangent line?
This is called the tangent line problem. We're not actually going to be calculating really very many things in section 1.1. I'm just showing you the problem of calculus. The problem was to try to find the slope of that tangent line. How do we do that without calculus? Well, one way is we can approximate it using this limit process, which we'll see not today's lesson. We'll talk more about that on Friday. The limit process in some cases is an approximation, in some cases is exact. But I don't want you to worry right now about having to do calculations and things. This is just an introduction to limits and changes and things like that.
That's a limiting process of going from the secant line all the way to the tangent line.
That's an example of a limiting process. And this phrase right here, as Q approaches P, the secant line approaches the tangent line. That's exactly the type of terminology we're going to use when we start talking about a limit. As x approaches C, f of x approaches blank. So that's like the first half of calculus. That problem right there, trying to find the slope of a tangent line, that really dominates the first half of the study of calculus. That's called the derivative. This problem right here will introduce us into the second half of calculus, which is the integral. Here's the problem, the area problem. A second blah blah blah. We don't need to really talk about that. Oh, I can barely see that. Can you see the color change on there? There's supposed to be an area that's in blue. Can you see it?
No, I don't want to see the Y.
The Y goes up and that.
There's supposed to be an area on my screen right here. It's blue. It's probably because of the light bulb. But anyway, you know what? I need to put this in a different program so you can see it. Hold on now. Whoop, whoop. This might work. Here we go. So I'm just going to draw on this. So what's supposed to be happening here is starting from point A, there's a line that goes straight up. Starting from point B, or value B, there's a line that goes straight up. This area underneath this is supposed to be shaded in. So draw that in your notes. We're trying to find the area of this region underneath the curve. This is called a bounded region. The top or upper bound is the curve, y equals f of x. The bottom or lower bound is the x-axis. And then it's bounded between the values a and b. Now, if you were paying close attention, when I scrolled over to the next slide, it kind of answered the question I'm about to ask you. So, if you did happen to see it, don't cheat. Let's see if we can come up with some ideas. I'm going to ask you the same kind of question I asked you last time. What would be a way that we could approximate the area? And I'm just talking about approximate. It doesn't even mean it has to be a super close approximate. Just some kind of an approximate of the area underneath this curve. Keep going.
So like,
Say that louder what you just said, though, by the way.
yeah, I would try to find the area of pieces.
Okay.
So like, I would probably start by trying to find a big, long chunk of rectangle first.
Like drawing a rectangle here.
And then you could find like the area of half a circle higher.
Like this portion here.
Yeah. You just guess what.
Okay. Well, that's not a bad idea. That's not a bad idea. Like this. Like a line of best fit going. Okay. 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 That's an interesting idea. That's an interesting idea. Let's go over here.
You like kind of do that, but like make it into a triangle. Sort of.
Like from here and then to here, and then like a triangle up here.
I know with the curve, like you have a point where one point of the triangle is on the line, and then so you've got one point of the triangle like on the line, and then the hypotenuse is close to the line of the curve as possible.
Okay, another interesting idea. Here's these are all great ideas. Here's, I don't know if this was the first idea ever. Here's was one mathematician's idea to at least approximate the area under the curve. Let's see, where are we? Section 1. And they're not that dissimilar to some of your guys' ideas. So here was one idea from a very early on mathematician. He was going to partition the region into intervals, okay, using rectangles. Now this wasn't actually a bad idea, because in order to find the area of a rectangle, what do you have to know? The width and the height, or the length, right? Now those we don't have to approximate. We can find those exactly. For example, we know the value of A, and we know the value of B, and if we partition that into 4 equal partitions, couldn't we figure out pretty easily the length or the width of all of these bases down here? So that would be pretty hard to figure out. What about the height of each of these? Do you notice exactly where they placed the corner of each of these rectangles? Right on f of x. So if I wanted to find the value of this point right here, all I'd have to know is the function's equation, right? And I'd plug in a to that function, that would be that point right there. So you'd know the height and you would know the width. Is this a pretty good approximation with 4 rectangles? It's pretty good, right? But isn't that one over there better?
Yeah.
Because now there are, what, 1, 2, 3, 4, 5, there's 8 of them. How could we get even more accurate? 16, or even more accurate. What is this process called? We're taking the limit, okay? This is a pretty good approximation. This is an even better approximation. But as you increase the number of rectangles, it says here the approximation tends to become better and better. The amount of area missed by the rectangle decreases. So the goal would be, if we do this an infinite number of times, instead of saying, well, we have 256 rectangles, if we keep increasing that exponentially an infinite number of times, that's going to approximate the area under the curve pretty good or very, very, very good. Very extremely good, right? This is called the limit process. Okay. As the number of rectangles approaches infinity, okay, that's this kind of a limit. As the number of rectangles approaches infinity, okay, the area of the total space approaches the area of the actual region that we're trying to find. And that is the end of the slideshow. So you're going to open up your homework and say, well, this is stupid. It is, I'm not going to say silly homework or waste of time. It is, and I want you to do it. It's going to present you with a situation. It's going to say, is this something you could solve using precalculus or algebra techniques, or is this something you would have to solve using calculus techniques? You have to really take a look, I guess. And for example, let me show you, or read it to you. We're in section 1.1.